excellent mathematician. Kolmogorov, who is also an excellent mathematician, made another theory of turbulence, and they have nothing to do with each other. They are completely unrelated. Now, I like turbulence theory as a subject because you can work there for a while and then drop the subject for 10 years and then go back. You still understand because things have not moved very much. So this is, in that sense, a good subject to work on. As a matter of fact, many people who work on turbulence start with the Navier-Stokes equation. So let me have this thing written down once and for all. I will not use it, but it's good to have it written. It says that the velocity of the fluid at a point differentiated by time is equal to v grad v. These two terms simply represent the acceleration. Now, on the right-hand side should be a force. This force is minus the gradient of the pressure divided by the density, plus a term here, nu Laplace v, which is a friction term. It would be absent if there is no friction, and then F is an external force. And I assume that the velocity of the fluid satisfies the incompressibility condition. The divergence V is equal to 0. Now, it's a well-known fact that this condition of incompressibility is such that you can project project along the incompressible flows, and orthogonal to that, and this is a term orthogonal to the incompressible velocity flows. So this gradient of the pressure you can ignore. You can project out this factor and study this Navier-Stokes equation. Now, an important remark, in my opinion, is that while this acceleration term is absolutely certain, the friction, the self-friction term, is in fact a first-order approximation. So if there is a strong self-friction, there will be further terms here that will come in. So it turns out that a lot of energy has been spent on this particular Navier-Stokes equation. However, other versions of the hydrodynamic equation, where you add further corrections to the friction term, are physically just as good. And so it's a mathematical idea to spend a lot of time on Navier-Stokes, and it is a very interesting equation. However, from a physical point of view, what you know is simply that there is self-friction, which means that energy will be dissipated on small scales. Why is energy dissipated on small scale? That's a dimensional argument. Small scales means that there is a lot of deformation on small scales, and then the energy is dissipated. Okay, so there has been a lot of work on this, which I mentioned in passing. The two-dimensional Navier-Stokes equation and the corresponding implicit equation have a good invariance and uniqueness theorem. For the three-dimensional Navier-Stokes equation, nothing is known. And people used to be sure that in the absence of friction, there would be a collapse of the solution after a finite time, but no, they are no longer sure of that. So very little is really known. And this does not worry me too much, because I will not really talk too much about this Navier-Stokes equation with this particular term. What is important is that energy goes from large scales. Usually what you do is you put energy in the large spatial scales of fluid, and there is an energy cascade down to small scales, and when you reach sufficiently small scales, then the friction term comes in and dissipates the energy. Okay, now, so I tell you as a fact that there is this energy cascade. Now you would want to ask me, why is there such an energy cascade from large scales to small scales? Well, there's a fact which I have not seen very much in the literature, although it is relatively obvious. You can, for a fluid which has infinitely many degrees of freedom, by making Fourier analysis or by using wavelets, distinguish degrees of freedoms which correspond to large scales and degrees of freedom which correspond to smaller and smaller scales. And it's not too hard to convince yourself that there are many more degrees of freedom associated with small scales than with large scales, like there's a 2 to the n or something. Okay? So, if you assume that you have, for the scales larger than some value, ergodicity, then this will mix, the energy will get mixed to the different scales. And since there are many more small scales than large scales, this means that if you put energy in the large scales, it will go down to small scales, and that is the energy cascade. So I have explained to you why you should expect an energy cascade. However, if you look at books on hydrodynamics and turbulence, you will find that there is a so-called inverse cascade in 2 dimensions. So why is it that I have an excellent argument that there should be an energy cascade down to small scales, and in 2 dimensions it seems to be something else? Well, this can be explained actually as long as you have no dissipation of self-friction, you have conservation of the rotation, I mean, the curl of the velocity. And this has the effect that the inviscid equations of motion in 2 dimensions have many conserved quantities. Well, if you look at the curl of the velocity at one point, this gets, the density of this gets carried away with the flow. In particular, the set of in 2 space, which has a certain curl, gets transformed into another set which has exactly the same curl. So that's a lot of conservation laws, and assuming ergodicity is completely inappropriate in 2 dimensions. So I want to talk here about 3-dimensional turbulence, where there is no evidence that there are conservation law, that ergodicity does not hold.
The Kelvin theorem. What about Kelvin theorem?
Oh, I mean, the fact is that if you put curve around some vorticity tube, then it gets carried away, but that does not amount to conservation law in the sense that it would prevent the ergodicity from holding. So there is something in 3 dimensions that corresponds to the conservation of vorticity in 2 dimensions, but while in 2 dimensions it breaks the ergodicity, in 3 dimensions it doesn't. I mean, you have to keep some conservation laws, but apart from the obvious, there is no conservation law. Okay. So, as I told you, Ruelle had a theory of turbulence which involved what Ruelle called turbulent solutions were solutions which developed singularities. At this point, one is not sure that there will develop singularities in the Navier-Stokes equation. So there may not be turbulence at all in the sense of Ruelle. The idea of Burgerbob is quite different. Burgerbob says there is this energy cascade, and it terminates when the energy gets to sufficiently small scales, and then it's dissipated. Apart from that, one has a situation that can be very well understood if one makes the assumption, apart from the equations of motion, the inviscid equations of motion, if one makes the assumption that turbulence is homogeneous, that it's everywhere the same. Now, I will not go into the details of the Burgerbob theory. It is in principle very simple. It is based on the fact that quantities of interest have some dimension in the sense of dimensional analysis, and the theory, the conservation laws, and the ideas about the cascade are such that basically, if you give yourself any quantity, you can guess its relations with other quantities on the basis of dimensional analysis. So it's an extremely robust theory, and it has given results which are remarkably in agreement with experiment. So the amount of energy contained in various scales has a description which obeys this dimensional analysis, and therefore there is not much problem with the Kolmogorov theory, except that the Kolmogorov theory assumes homogeneity, and homogeneity is not satisfied in practice. So if you look at the turbulent fluid, which is not easy to do because either it's opaque or it's transparent, but in any case you don't see the velocity. Now one can make numerical simulations and visualize things which are otherwise not easy to see. But what one sees is that vorticity, which is relatively easy to visualize in simulations, is concentrated in little clumps that divide into further clumps. And that's not in agreement with the idea that turbulence is homogeneous. So the contrary of homogeneity is called intermittency. So turbulent fluids are intermittent. Now, the problem is that it's not very easy to quantify this statement. Turbulence involves large dimensions, spatial dimensions, and to integrate numerically the equations of motion requires computational power, which we don't have at this point. The problem is that we want to see scaling over many orders of magnitude for the size of the system, and that requires computational power that we don't have at this point. So experiments are still important, and also studies that consider turbulence at a given Reynolds number. Reynolds number is a number that says roughly how turbulent things are. So one can study turbulence at small Reynolds number, but what happens at large Reynolds number is still a difficult problem. So experimentally, what happens is if you put energy into the large wavelength of a fluid, it will go to the small wavelength and get dissipated. And if you don't excite your system enough, you have so-called laminar fluid flow. And if you put enough energy in the large scales, then you have turbulent flow. And it's your problem to decide what is turbulence. I mean, you can go to the bathtub and make your own experiments, but that does not give a theory. And the theory of Kolmogorov simply lacks this ability to deal with intermittency. Okay, so now a number of people have worked on the problem of intermittency. The data which one has obtained by lab experiments are not of very great precision, and it is relatively easy to make an ansatz depending on some parameter that fits more or less the data. So what I will present to you is one theory that does give a good fit to the data, but it has ideas behind which are physically satisfactory, and I will therefore present these ideas. And what one tries to obtain is a distribution of the intermittency coefficients, the intermittency exponents. Now, what happens is if you take a turbulent fluid and look at a given small length in the fluid and at the change of velocity over this small length, the piece power of the change of velocity is in the average something that goes like the length to power zeta p, and zeta p is called intermittency exponent. Now, the Kolmogorov theory gives an answer for the zeta p, and since it was not adjusted, it turns out that it does not fit the data. So one knows that one has to do something better than Kolmogorov to get the zeta p. Now, what I will try to do is to present to you, not in great detail, but I think sufficient detail, an expression, a derivation of the vorticity, of the intermittency exponents, which is p over 3, this is the Kolmogorov term, minus 1 over log kappa, this is just a constant which I adjust to be like 0.32, logarithm of gamma, this is the gamma function of p over 3 plus 1. So this is just an expression of which you have to believe me that it does give a certain fit to the experimental data which are obtained in a large wind tunnel. Now, there is one fact which to the experts appears significant. If I take p equal to 3, namely I look at the third intermittency exponent, p over 3 is 1, and gamma of 1 plus 1 is 1. I mean, it's factorial 1 and it's 1, and therefore the logarithm here is 0, and this means that for p equal to 3, one has 1 as a value, which has somehow been found to be correct, at least. I mean, people working seriously with Navier-Stokes equation, which I'm not doing, have come to the conclusion that this is the correct value for p equal to 3. So that carries some weight with professionals of Navier-Stokes equation, although I would not attach too much importance with the fact. Then I will say a few more words about the radial velocity increment and the relation with the so-called Kolmogorov theory, and then mention that with this value of log kappa, one gets onset of turbulence at around Reynolds number equal 100. So the Reynolds number is the velocity, is a velocity times length, say the size of the volume in which you put your fluid, divided by nu, nu being the viscosity coefficient. So that is not a very well-defined quantity, because should you use the diameter of the place in which you put the fluid, or the radius, I mean, there's a factor of 2. But Reynolds numbers are usually large numbers, and a little factor of 2 is not too important. Okay. So what does it mean that Reynolds number is around 100 at the onset of turbulence? Well, that means that if you have a system in which there is no force depending on time, you will probably get a laminar solution independent of time up to a certain value, and then there will start to be sensitivity to initial condition, which would arise at about 100, independent more or less of the geometry of the thing. And this is not experimental result, this is a computational result, because this means that one has studied hydrodynamics by numerical methods which are appropriate for this sort of thing. Okay. Now, how does one get a theory of turbulence? Well, the picture which I shall try to use is the fact that there is in a turbulent fluid, there are in a turbulent fluid so-called eddies, which, if you believe that there is intermittency, is regions where something happens. So there is something which happens in an eddy, and then you have some space, and then another eddy, and then different eddies. And these eddies have a lifetime. So you start by putting energy in the whole volume, and so you have, if you like, just one eddy, and then after a certain time, this eddy decomposes into eddies which are separated into the volume, and so on. and so forth. So the idea is that I would like to describe probabilistically the decomposition of these eddies. Now, one thing to have in mind is, since there is intermittency, the region of space, physical free space, in which something happens becomes smaller and smaller. I mean, the portion of physical free space in which something happens becomes smaller and smaller as you get to eddies of higher and higher level. So this is not at all something homogeneous in time. There is a non-homogeneity in time as there is in space. So you should not try to make theory to fit data with a theory which is homogeneous in time. Okay. So let's see. We have a big box, and after a certain time, this box will be decomposed into a number of sub-boxes, and I shall make the assumption, which one can discuss, that these sub-boxes of level n are roughly of the same size. They are roughly polyhedral things that contain an eddy. And we want to understand how the energy goes from one level to the next. So at level n-1, there will be regions R n-1I, which have a certain kinetic energy. And then these eddies will have a lifetime, which I indicated as T sub n-1 I. Now, at the next level, you will have in boxes of size R and J eddies with energy E of R and J that will last for a time T sub Nj. Now, the energy therefore goes from one level of eddies to the next level of eddies, etc. And it stays in a certain level for a characteristic time T sub Nj. So the energy contained in this eddy of level n-1 gets to the energy in level n, and the sum of the energy contained here, which lasts there for a certain time, goes to the next level, and the speed at which it goes is E divided by T Nj. So I'm saying that the energy is conserved when you go from one level of eddies to another level of eddies. Now, there is a relation between the velocities at a certain level and the size, L and J, and the characteristic times, which is forced by symmetry of by the fact that energy is conserved, and there is some scaling of the basic equations of motion that forces this relation to be true. Therefore, we can rewrite this equation in terms of the energy is the velocity squared up to 1/2, but since one divides by time, it's the same thing as dividing by the length and putting an extra factor of v. So this means that this can be rewritten as sum over j of v cube divided by L summed over the sub-boxes is the same thing as this thing. So you have the conservation of energy, and I shall make a simplifying assumption that the length, the characteristic length, the size of the boxes at a certain level is like kappa to the power n. Now, obviously, I'm now making assumptions which are approximately correct and not completely correct. This is different from the attitude of Kolmogorov, where he says there is turbulence is homogeneous. So saying turbulence is homogeneous is a clean statement, and you cannot dispute it except saying that it does not fit the experimental data. Now, if you want to change this assumption of homogeneity, you have to change it in some specific way and to make assumptions that will be approximate. So the idea is that we have something which is approximate. Now, if we look at this thing here, it says that the integral of v cube divided by the size. Okay, so let me rewrite this. If I use the fact that Ln minus 1 j over Ln j is equal to kappa, I can replace this by okay, let me and Lj Ln over is 1 over kappa. So essentially what we have is that we have conservation up to the splitting of something like v cube. Now, this means that in these boxes, in these sub-boxes of level n, the sum of the V cubes, here I'm not giving all details, but trying to give an idea. The sum of the V cubes is a constant given what exists at level -1. Now, there are many possibilities to have a decomposition of some V cube into different pieces with given sum. Now, in equilibrium statistical mechanics, what one does is one looks at configurations with a given total energy, and one looks at what one gives a certain weight in configuration space or in phase space that is proportional to the volume of the thing in question. And then one obtains the so-called microcanonical ensemble, which says that space is occupied proportionally to the volume in phase space at given sum of the energies. Now, in statistical mechanics, it is known, and this is in fact a mathematical theorem, that this microcanonical ensemble is approximately the same thing as the canonical ensemble. So it turns out that distributions that give the same total energy are distributed like exponential of minus an inverse energy times the quantity in question. So that's a natural choice, which means, roughly speaking, that one maximizes, that one looks for distribution that maximizes entropy. So occupying uniformly volume in phase space or using the canonical distribution exponential of minus beta times the energy is approximately, gives approximately the same thing. Now, the energy I replace by V cube, and here there is a D3V, and so it comes natural to look at the distribution of the V cube, which we call big V n, and this is then given by beta exponential minus beta Vn dVn. So there's something slightly subtle there, which is that the dV comes with comes to the cube. You have a d3v, and if you had a dv, d2v, you would not get this result. But in any case, that's what one gets, and it is a natural assumption to say that given Vn minus 1, the distribution of the Vn corresponding to vortices of the nth level is given by such an expression. And you should find what beta is, and beta is given by the fact that you have conservation of the V cube when you split between different boxes. And let me try to okay, so this relation actually should be kappa over V n minus 1 exponential minus kappa Vn over Vn minus 1 dVn. Now, what happens is you start with a V0, which is the energy put in the big box, and then at the level of 1 eddies, you get a distribution of V1, and then V2, V3, etc. So actually, what one should do is take a product of such things with n equal 0 to some large n. So that is, in fact, the law of probabilities which I assume for my eddies. It is a cascade, and this cascade is not completely uniform in the sense that it is intermittent. I mean, if you look at eddies of a certain level n, and if you look at them carefully, you will see at what level you are from the point at which you did put the energy. And then, now, having this formula, which is completely explicit, you can study the distribution of the, I mean, you can identify Vn as the velocity difference at level n, and you can therefore take this thing, apply it to V sub n, and since these integrals are simple, and they are, I mean, what you integrate is an exponential times some polynomial, and these give gamma functions. So it is believable, and I will not try to make an exact calculation, but it is believable that you find such an expression for the zeta p. Okay, so that's one result, which is the first thing that convinced me that the idea was not completely wrong. The value of log kappa is unexpected, because it means that from one level of eddy to the next, you have a factor of about 20 in size. So that's a very large factor, but it does fit the data. Now, what can one do with that? It is possible to estimate the radial velocity increment. I mean, what you say is the velocity increment corresponds to one given size of eddies, namely n, and you make a simple integration, and you find a certain result, which perhaps I shall not write down, but it gives that the radial distribution at size n is given with suitable variables as a convolution product of n terms. In fact, this corresponds to what Kolmogorov and Abukhov introduced as a log normal thing. So what you do is you have, I mean, I'm not giving the details, but just giving an idea. When you go from one level to the other, you have a product distribution which is normal. So when you add things independently, you tend to have a normal distribution, a Gaussian distribution. And when you multiply things independently, you tend to have a log normal distribution. And there is a theory of Kolmogorov and Abukhov where they were told by Landau that they should try to look for intermittency because Landau had some idea that it must be present, and it was. So the natural idea of Kolmogorov and Abukhov was to have structure, a cascade structure, which reproduced, in fact, a log normal distribution, which is what we sort of find. I mean, we do obtain something like this. Now, it's known that the log normal distribution of Kolmogorov and Abukhov is wrong. It does, in fact, not give the appropriate intermittency exponent, and it's physically not satisfactory. However, the notion of Kolmogorov and Abukhov was to have a product of independent quantities that would, when taken the logarithm of, give a Gaussian distribution. However, when you add independent quantities, you do not necessarily get a Gaussian distribution. You get a Gaussian distribution if the things that you add decay rapidly at infinity. Now, it turns out, and one would have to look at the details, it turns out that the things that one adds according to this approach are things which decay exponentially at infinity. And exponentially is not good enough to have a log normal distribution. So one gets with this approach a better, I mean, the fact that one gets intermittency exponents which fit the data and Kolmogorov or Burgerbob do not fit the data is probably simply an incorrect application of the log normal distribution. Now, the last thing is one can, with all the formulae that one has, estimate at what Reynolds number, namely this thing, the first order eddies come into existence. I mean, what can happen is that by the time you get the first order eddies, this term here has already killed the eddy, so one never sees the first order eddy. So the problem to speak of the onset of turbulence is when does one have a sufficiently high Reynolds number that the first order eddies are not killed before they come into existence. And this gives something like 87, and it fits the numerical data that exists. So this is not proof where you finally compute something with several decimals. That's not a domain where one has several decimals, but it does fit roughly the data. So I will stop there. Thank you.
Questions?